Welcome and hello. This is a video exercise using HEC HMS. And in this exercise, we're going to be working with the applying and sampling of NOAA Atlas 14 temporal patterns. All right, what I have on the screen here is a list of different exercises for flow frequency simulations. If you scroll down a little bit towards the end, we have these two for applying and sampling the NOAA Atlas 14 temporal patterns. So this is what we're going to be doing in this exercise is these two. I'll call it part one and part two. Let's go ahead and get started. I will leave a link to these two exercises and the pages here in the description of the video. Make sure you have version 4.12 or more recent. It says 30 minutes. Let's make it a goal to break that time. And then let's download the initial project files here. Click download. Okay, so that was downloaded right there. Here's the zip file. Let's see what we got. Cottonwood Creek. And now here are the files and folders I expect to see inside of an HMS project. So I'm going to move that into my computer where I want to keep it for real. All right, let's go to HMS and then open that up. Click on the Browse button. Here is my project, Cottonwood Creek. So I'll click that and then click on this .hms file and select. All right, one thing I like to do is just bring up the basin map here so I can see it on the basin model panel. This particular watershed is in Arizona. So what I'm going to do now is visit the NOAA webpage to download the temporal distribution of rainfall in this area. And then we'll come back to HMS and then continue the exercise. So if we go to the webpage here, we have an introduction. Here's the study area. You can see there's different junctions. There's the map of Arizona, and then download data. Okay, so this is where we're at now. There's a link here I'll leave in the description for NOAA's Precipitation Frequency Data Server. I'm going to open that up in a new tab here and then click on Arizona. Okay, so what I want to do now is just scroll down to the Supplementary Information tab. Click that, and then scroll down further until we get to Temporal Distributions. Now our options here is 6 hours, 12, 24, and 96. I'm going to click on 24 hours and then click Submit. What that's going to do is download a .csv file. Okay, looks like it's done already. And then let's move this into the data directory for our project and take a look at it. So Cottonwood Creek, here's the data directory. We already have some data in this project, so never mind that. Just drag that CSV file over. And let's go ahead and take a look at what's in this file. Okay, here's an explanation at the top. I think it's pretty helpful to understand. But basically what we're seeing is the cumulative precipitation of a storm event for different storm patterns. So the first quartile data here represents the storm pattern where more precipitation falls in the first quartile or first 25% than the other three quartiles. And then for the second quartile, that means there's more precipitation that falls during the second quartile than any of the other three quartiles, and so on. Third quartile, fourth, and then all cases. The first row of data right here represents the percentage of time of the storm. So every 8.3333%, I believe, or approximately that. And then 10%, 20%, and so on. So what we're going to do is just leave this right here in our data directory, and we're going to go back to HMS. All right, back in HMS, I'm going to click on the Tools menu, Data, and then Atlas 14. For part one of this exercise, it's going to be Temporal Pattern Importer, and then later, for part two, we'll be dealing with this Value Sample Creator. Okay, so Temporal Pattern Importer, what we're going to be doing is importing percentage curves. So before I do that, let me just go ahead and show you that in our paired data manager, all we have is area reduction functions. We don't have any percentage curves yet. So that's what we're going to be automatically generating by using this importer tool. Okay, let's actually do it now. Tools, data, Atlas 14, import those temporal patterns. Now it's looking for a CSV file. Let's go ahead and find that CSV file. Here is the project. Here is the data directory. And then this top file right here is the one we want. So I'll click open. Okay, click next. So it's automatically detected the different quartiles. We're going to select all four, 1, 2, 3, and 4, but not all cases. Click next. Where we're going to save this is external DSS. And then I'm just going to take a look at the file here. Okay, so that's the file. Then I'll click next. The import's complete. Let's click close. And now let's go back to our paired data folder right here in the Watershed Explorer. And what we have percentage curves. These percentage curves represent that storm pattern, the temporal distribution that we downloaded from the NOAA website. I'm going to go ahead and look at a few of them, or at least one. We're going to click on quarter to 50 percentile right here. So we have the data, and then we can also look at it in a graph form. Remember, this is the cumulative precipitation on a percentage basis based on the percentage of the storm duration. So this Q2 second quartile means that there's more precipitation fell from this 25% up to the 50% than any other quartile, which is pretty obvious if you look at the plot. We can also look at the tabular data, 75.3 minus 25.7. So it's yeah, almost 50% of the precipitation fell in that second quartile. All right, the instructions next tell us to run the simulation. So some of this has already been set up for us. In compute, we have this simulation run called hypothetical 100-year 24-hour storm. I'll click on the compute. Oops. I need pattern is not set for user specified storm. Okay, one second. All right, yeah, I forgot to do that. In the meteorologic model, I'll go back to meteorologic model, click on hypothetical storm. Now for the storm pattern, I'm going to select the pattern that we just saw on the screen, which was Q2, 50%. Everything else here is set up as we want. Some of this data was already part of the project when we downloaded it. Save and run the simulation. Okay, I wanted to check the control specification just to see what we computed here. We have a control specification for 72 hours. So if I go up to control specification right here, it's labeled 72 hours. It's only 48 hours, but it's in the future, so maybe math is different there. It's a 1 hour time step over 2 days, 48 hours. Okay, let's go ahead and view some of the results from that simulation. I'll click on the results tab and then expand the simulation runs. If I want to look at, like, for instance, one subbasin, S1, I can click on that and then click on the graph here. And what we have is a Hayedo graph on top, which shows the precipitation and excess precipitation. And then on the bottom, we have the flow rate, which is the hydrograph, where we have the total flow and then the base flow contribution. We can also look at the similar hydrograph at the outlet in the results tab. Should be an outlet. You know, it's easier to just right click and then view results graph. So here is the outlet results. Looks like a peak flow of around 12,000 CFS. I'm going to take a look at the subbasin data real quick. And I noticed that it's not only discretized, but it's using Mod Clark, which leads me to believe we can run the same simulation and view spatial results as well. So let me see if that's true. Compute. And then let me select this computation. Yeah, it looks like we can. 1 minute time step and save. Let's go ahead and run it one more time. This is not part of the exercise. This is just me being curious. All right, cool. So let's go ahead and check out incremental precipitation. That would be a good one. And click OK. If you don't have this spatial results toolbar, you can go up to View, Toolbars, and then Spatial Results. I'm going to toggle off my 2D. I don't need that. All right, so let me change the scale here. So I think the maximum precipitation here is 0.008. Let me just do a couple other samples, 0.008. So maybe 0.01 would be a good maximum. Yeah. Okay, I'm going to change the top range real quick. I'm going to also speed it up. Sorry, I meant stretch. 0.01, apply. All right, apply and OK. So this is a 24-hour storm. So the second quarter would be between 6 a.m. and noon. That's when we're going to have the most precipitation. Okay, let's go ahead and play it now. So it's 0 o'clock, 1 o'clock, 2, 3 o'clock, 4 a.m., 5 a.m., 6 a.m. Okay, now between 6 a.m. and noon right now is when we're going to have the most precipitation, which is going to be, yeah, like our yellows and reds. It's 9 a.m. right now. That's 10:30 a.m., 11, and then at noon right now is when it starts to level out and there's less incremental precipitation. Okay, so if I drag that all the way to the end of the 24-hour period, we're basically have no precipitation again. All right. Well, that was it for the first exercise. I don't think that took half an hour, but it was good. Let's go to the second exercise now. So if I go back to the instructions, you can just use the breadcrumb navigation and click here, and then go to the second option for sampling NOAA 14 temporal pattern. Here is the exercise. I will also leave a link to this page in the description of the video. All right, you can go ahead and download the initial project files here, which I'm not going to do because I already have the files up and ready to go in HMS. Here's an introduction. Here's the same study area. They could really have made this one exercise. All right, so what we're going to do is create a parameter value. Let's go back to HMS here. Go Tools, Data, Atlas 14. Now this time we're going to select Parameter Value Sample Creator. What we're going to actually be creating using this tool is parameter value samples, which is a type of paired data set. So let me backtrack a little bit. Click on the Components menu. I'm going to actually deselect or select none for my spatial results so it's not as distracting. And then if I collapse the basin model down in paired data, what I have is percentage curves and area reduction functions, but I don't have any parameter value samples. So that's what we're going to generate using our percentage curves. Okay, so I'll go up to Tools, Data, Atlas 14, Parameter Sample Values. For this drop down here, the parameter is going to be a storm pattern. And then what I'm going to select is all the Q3 patterns, just as an example. So quartile 3 starts here at 10%, hold down Shift, and then click 90%. It highlights all the intermediate records as well. Click the greater than symbol, and then next. Okay, for the name, I'm going to call it Q3 patterns. Click the next. Project DSS file, that's fine. I'll click next. And then it says complete, so I'll click close. Now let's go back up to our Watershed Explorer and click on paired data. Now we have this whole folder for parameter value samples. So we have our Q3 patterns right here. And if I click on the table, you see values, index values 1 through 9 reference those storm patterns that we have up here in the percentage curves. The next part of the instructions tell us to run the uncertainty analysis. And because I'm using right here, because I'm using the project files from the first example, then there's a few more steps I need to do to set it up. So just hang with me here. Let's go back to HMS. What I need to do is create an uncertainty analysis. So I'll go up to the Compute menu, Uncertainty Analysis Manager, New. I'll give it a name, which is Uncertain Q3 Time Pattern. Click Next, and then we'll use our basin model, our one and only MET model, and done. All right, next let's click on the Compute tab in the Watershed Explorer, expand our uncertainty analysis, click on our analysis we just created. Now there's a few things we need to do here. So for analysis points, click on this gear option and then click on the outlet. Okay, save and close. So that's been selected. I can go back and confirm that it's selected by just confirming that the checkbox is still checked there. The basin model and MET model is fine. For the start and end date time, I'm going to use the same 72-hour period, which was actually only 2 days. So January of 2099 till January 3rd of 2099. Okay, it'll be a 1-hour time interval. And then for total samples, it will be 100. I'm going to leave this seed value as it is because that's a random number, a pseudo-random number. Okay, next I'm going to add a parameter. So right click on that uncertainty analysis, add parameter, click on that parameter 1 icon. And then for the element, I'm going to select precipitation patterns. The parameter is going to be hypothetical storm pattern. The method is going to be random, independently random. And then the last one for parameter value is going to be Q3 pattern. That's our only option. All right, so I'll click save. Now I'm going to run that uncertainty analysis. It's already selected up here in my compute toolbar. I'm going to go ahead and run it. This may take a while. It's going to be 100 iterations or samples. Okay, so that finished up. That looks good. Let's click on the results tab here and then expand that uncertainty analysis data right here. All right, so now I'm going to look at the parameter data first. What we have here is the number of samples. There should be 100 on this table, and there is. The parameter is randomly selected. So what that means is for each of the 100 samples, we should have a different outflow. Well, there's only 10 samples or 9 samples, but so what we're seeing here is the hydrograph of the outlet. It's an uncertainty analysis using that Q3 pattern. All right, so we have a mean value that's in solid, but then we kind of have some lighter lines representing the minimum, maximum, and then the mean plus and minus the standard deviation. Looks like the maximum flow is right just above 14,000 CFS, but then the average flow is just below 12,000 CFS. If I'm curious which storm pattern generates this highest of 14,000 CFS, we can dig down into the data. So maximum flow right here, here's that 14,000 record. And then I could just trace it back to being record number 6 or sample 6, and then go back up to the parameter and sample 6 is the 90 percentile Q3 record. So I should probably be able to find that a few other places if I scroll down and look for 90%, like right here, for instance, sample 49, and then close that. The maximum value for sample 49 is right here. It's, again, 14,270. We also have results here for outflow volume for all the different samples. Well, that was it for the uncertainty sampling exercise. You can go ahead and perform the same analysis on quartile 1, 2, and 4. That's what the instructions tell you to do. But I think this lesson demonstrated at least how to do it. So you can go ahead and do those on your own if you like. The results for the outlet hydrograph for Q1 look like this on the screen. And then there's also a similar plot for Q2, Q3 like we saw, and then Q4 right here. Well, that is it for this exercise. We did some applying and sampling of the NOAA Atlas 14 temporal patterns in HEC HMS.